Today, I'll present GraphTreeGen, Subtree-Centric approach to efficient and supervised graph generation. First, let's cover some preliminaries. In the brain connectome, represented as a graph, we have nodes corresponding to brain regions of interest, and edges representing the connections between them. In the tree structure, we have a root node and leaf nodes. Within a graph, a tree-structured subgraph can take on various shapes and configurations. For example, the green node and the blue node in the graph have a tree-structured graph like these. A generative model uses an encoder to learn a latent representation of the data, then a decoder to generate new samples from that representation. Graph neural networks are ML models designed to process graph-structured data through recursive neighborhood aggregations. This is an example of one-hop aggregation. The brown node in the center gathers information from its immediate neighbors. Now, let's talk about limitations of generative models on graphs. First, some models compress the entire graph into a single latent code, thereby blurring fine-grained local motifs. Second, most generative models rely on rich node attributes that brain connectomes typically do not provide, which diminishes reconstruction quality. Third, edge-centric models like dual graph frameworks emphasize topology but often overlook the accurate prediction of edge weights, sacrificing quantitative fidelity. Fourth, many state-of-the-art architectures, such as those using edge-conditioned convolutions, employ computationally expensive architectures, which results in significant memory demand and limits their scalability to larger connectomes. How to learn both topology and weights of the graph efficiently. Here, we propose the method GraphTreeGen, Subtree-Centric Graph Generative Model. Why do we use trees? First, subtrees serve as reusable motif tokens. This imposes a structural prior that highlights recurring patterns, communities, stars, and chains, gives more structural information for further learning. Second, operating on small subtrees scales roughly with the same of the edges within a tree, instead of the potential n-squared complexity of full graph message passing. Third, this tree structural bottleneck forces the model to summarize motif combinations rather than copy entries, yielding robustness under edge masking, noise, and preventing trivial identity mapping. Here's an overview of our GraphTreeGen model architecture. Let's go over this step by step. First is the tree encoder block. In this block, we input the brain connectome graph. We want to learn a good representation of the graph. How to learn structural information. Here, we come up with the idea of subtrees, which can capture the local structural information of the graph. We hope to get the embeddings of these subtrees to represent our input graph. How to find the most representative subtrees in a graph. Based on node entropy, computed from node degrees, we identify the top nodes with the highest entropy and set them as root nodes. We then collect their one-hop neighbors to form a set of subtrees. We then pass these subtrees through a shared GCN block to learn their embeddings, preserving the structural information. The second part is the cross-tree aggregator. After obtaining these tree embeddings, we project both the tree embeddings and the node embeddings into the same space for joint learning. This raises another question. After capturing the structural information, how can we accurately learn the edge weights? Here, we create a bipartite graph between subtree root nodes and the original nodes to let them talk with each other. Each root node of the subtree is connected to their leaf nodes in the original graph. In this way, the bipartite graph bridges subtree and node embeddings, enabling multi-scale information exchange, injecting motif-level priors, and achieving efficient, linear cost message passing. We learn the bipartite graph using the GCN block and get the updated embeddings of the nodes and trees. Finally, in the pairwise decoder stage, the updated embeddings are passed through two MLP blocks. One learns the graph structure by predicting the existence of edges, and the other learns the corresponding edge weights. This pairwise design explicitly models both structure and weight, ensuring a more balanced and accurate generation process. Here's our experimental setup. We evaluate our model on 341 brain connectomes from the Byte1 dataset, including 186 neurotypical controls and 155 individuals with autism spectrum disorder. Each connectome is a 35 × 35 symmetric adjacency matrix without self-loops, derived from pairwise absolute differences of cortical morphology across 35 ROIs. For the training settings, we use 5-fold cross-validation and trained for up to 100 epochs and with early stopping. Here are the benchmarks. The first one is Iman GraphNet. The second one is STP-GSR. And the third one is VGAE. We also compared our method with BonsaiGen, a generative extension of the Bonsai graph condensation algorithm, which we defined. The results are evaluated using 10 comprehensive metrics spanning edge-level accuracy, node centrality preservation, and global structural consistency. Here are the results. For self-supervised task, we can see that GTG outperforms all the benchmarks, and only one metric slightly lower than BonsaiGen. Here are the visualization of the adjacency matrix of all the models, including ground truth, generated adjacency matrix, and residual. The first one is the Iman GraphNet. Second, VGAE. The third is STP-GSR. Fourth, BonsaiGen. And the last is our proposed method, GraphTreeGen, which is the best performance. We also evaluated our model on a supervised task, and both the visualization and the table show that GTG demonstrates comparable performance to all other methods. For the memory usage, GTG significantly reduces memory usage compared to most of the baselines except BonsaiGen. However, BonsaiGen performs notably worse than GTG in generation quality. In conclusion, GTG offers an efficient graph generation framework that operates with significantly lower memory usage while preserving both high-quality structural patterns and accurate edge weights. By leveraging subtree-based motif priors, cross-scale information exchange through the bipartite design, and a pairwise decoding strategy, GTG balances computational efficiency with generative fidelity. Beyond the current setting, this framework can be naturally extended to graph super resolution, where low-resolution graphs are upsampled to richer, high-resolution counterparts, and to cross-modality generation, enabling structural information learned from one modality to guide graph generation in another. Such extensions open up promising directions for applications in brain connectomics, multimodal networks, and other domains requiring efficient yet expressive graph synthesis. This is the end of the presentation. Thank you so much for listening.